Okay, we are wrapping up this unit with residual plots. These are related to the regressions that we learned about last time. Remember, we use regressions to make predictions. So when we know the actual value, we can compare it with the predicted value, and the difference of the two is called a residual. So for example, here I have the linear model that we derived last time for the weight of the baby after birth. So if we recall the predicted value at 2.5 months, I plug in 2.5 into my function for x, do my calculations, and I got 5.34 kilograms. Now, if the actual weight of the baby at 2.5 months was 5.5 kilograms, the residual would be the actual minus the predicted. So the actual was 5.5 minus my predicted 5.34, and I get 0.16 is my residual. Now, what this means is I underestimated the weight. If I end up with a positive residual, that means you were under. If you end up with a negative residual, that means you were over. So in that same spirit, let's look here at this example 2. The number of cars in the U.S. grew exponentially after Henry Ford utilized the assembly line process. And so here we've got a data table with the number of cars per 1,000 people for some years after 1920. So first we want to use a regression to find an exponential model for the number of cars. So this is where you need your calculator if you don't already have it. And we are going to put those x values, our years after 1920, into list 1. And then our y values, the number of cars per 1,000 people, into list 2. And it tells me we're going to do an exponential regression, so I'm going to go to stat, calculate 0 for exponential regression, and my function is going to be 120.09 times 1.03 to the x power. And now I'm going to use that to find the residual for the number of cars per 1,000 people in 1980. So remember, this is years since 1920, so for 1980 that would be 60. Now, I have the actual value in the table here, but I need to find the predicted value using my exponential regression. So I'm going to use that to calculate when x is 60. And I get 707.52 for the predicted. So if I subtract that from the actual value, my residual is 2.69. And again, that was an underestimation. Moving on, for 10 weeks, Jasmine kept track of the number of coffee drinks she purchased each week, and here is the total amount of money she spent. She found the linear regression of the data to be this, so she already did that hard work for us. Construct a residual plot. So what a residual plot is your x values are still the same, but your y values are now the difference in your original minus your predicted. So we are going to use a list to calculate those residuals for us. So in my list 1, I'm going to go in and put those coffee drink values. And notice we do have some repetition here with x values, but that's okay because these are scatter plots. They are not functions, so they don't need to pass our vertical line test. Okay, I got off somewhere. 2469, here we go. Not sure how I got that so backwards, but Ah, 50.49. Okay. Hopefully you make less errors than I did. Okay, so you've got your x's and your y's. Now what I want in list 3 is to put this function, and I want it to pull the x values from list 1. So what you're going to do is in list 3's column, arrow up, and hit enter. Once this starts flashing, we're going to enter that function. So that's 3.05 times, I want it to multiply the values in list 1. So I'm going to go to second list and call list 1, then add 2429, and it will calculate all the predicted values for me. And then what I can do in list 4 is calculate my residuals. So again, arrow up, hit enter, and I want it to do list 2, my actual values, minus list 3, my predicted values. And there are my residuals. So I can copy all of those values into my table, and then we can plot those points. Again, this is a scatter plot, so it does not need to pass the vertical line test. You will have some repetition with your X values. And again, I'm just going to go through one at a time, and this one's going to be a little bit off the graph. 8 is at -10 and change. And you are welcome to skip ahead if you don't want to sit here and watch me graph all of these. Okay, so there is my residual plot. Let's move on to example 4. A scientist is studying the relationship between the speed of a vehicle in meters per second and its braking distance. The table below reflects data collected. Use a regression to find a quadratic model and then construct a residual plot. So we're going to do everything we did on example 3, but instead of being given the model, we are going to have to calculate that ourselves. So I am first going to put my X and Y values into list 1 and list 2. And then it tells me that I need to do a quadratic regression, so that is what I'm going to do. And my function is going to be y equals 0.2x squared plus 0.98x minus 0.6. That is the function I'm going to use to do my predicted values. I'm just going to delete everything out of both of those. And in list 3, I'm going to put 0.2 times list 1 squared plus 0.98 times list 1 minus 0.6, and it will do my predicted values for me. Then I want my residuals, which is going to be list 2 minus list 3. And I've got a new set of residuals that I can plot on the graph. And I don't have any repetition with my X values this time, so it's going to be nice and easy. And this graph works out quite well as far as the increments, which is nice when that happens. We don't have to do any guesswork. Okay. Moving on to the last page for this section, we are now looking at bacteria growth. So we are going to do an exponential regression and get our residual plot. So back to our handy dandy lists. Oh, just 5, 0, 1, 2, 3, 4, 5. Okay, then I'm going to do an exponential regression. And my function is going to be 100.34 times 1.49 to the x power. I'm going to have my calculator do the heavy lifting for me, and in list 3, after I delete all those old values, I'm going to say 100.34 times 1.49 to the list 1 power. So there are all my predicted values. Then list 4 will be my residuals. List 2 minus list 3. And once more, I can plot those points. I'm just going to round each of these to 2 decimals because they are not very pretty this time around. And I'm just going to eyeball these. Oh, and that would be here, actually. That was an oopsie. 2. Okay, final question for this section. A student is analyzing the relationship between the number of months a product has been on the market and its monthly sales. Here we've got some data. So first we need to determine the kind of model that it is. So I'm going to graph that in Desmos. And here I have those points. So I know it's not linear, but here comes the trick. Is it going to be quadratic or exponential? So I did a regression for both, and I have those equations here. You're welcome to do that in your calculator as well. Here is the exponential. If you look at the fit, it is pretty good, but it's just barely missing 2 of those points. If I do the quadratic instead, it does appear to be a better fit. So I am going to go with the quadratic model for this example, and I'm going to calculate my residuals. So if we go with quadratic, and my function is 0.58x squared plus 0.03x plus 4.71. I can have my calculator do all the heavy lifting for me once again with my x's and y's in list 1 and list 2. Then in list 3, I want my predicted values. Then my residuals in list 4. And I can do my last residual plot. And there we go. I'm just going to get all those on my graph. That one's way up here, too high. Oh, so is that one. Okay, my graph is a little off here, but you get the idea of graphing each of these. And I trust that you could graph it quickly. Let's talk about residual plots and how we know if we have an accurate model. So if I use a regression to get a model and I plot my residuals, in order for me to clearly say that I had a good model to represent my data, there needs to be no pattern evident in your regression. So if we look at these 3 examples, if I used a residual plot for the linear regression, this was my graph, and if I used a quadratic regression, this is my graph. Notice that these are following a sort of pattern. We clearly have some sort of correlation here. That means that neither of these were good models. And if I move over here to the exponential one, the way it bounces back and forth with no clear pattern, that means this was the winner. So looking at example 2, if I have a regression for this graph, and this was my residual, that means they did not use the correct one the first time around, again, because I have that pattern. So if, let's say, they had used a quadratic this time, that means I want them to use an exponential to get it correct. Another example, if we used a quadratic regression for this set of data and this is my residual, I know that this is not a clear example of the correct model, so that's going to eliminate answer choices 1 and 2. It is not an appropriate model. And why do I know that? Because it shows a quadratic pattern, which I don't want to see. Another example like that, we use an exponential regression for this set of data, and this is my residual. Notice there is no pattern, so that tells me this is an appropriate model, so I can eliminate A and B. And I know it's appropriate because the results show no pattern, so C is my correct answer there. And then one last conceptual thing, we've got a guy that's painting a mural to try to break the world record, and he wants to paint a bunch of circles. And what we want is a model to determine how much paint he needs depending on the radius of the sizes of the circles. Now, we are looking at radius, R, and what do we know about circles? Well, we know the area of a circle is pi r squared. So the radius to area relationship is going to be squared, so that tells me that I want a quadratic. For this reason, as well as if I'm looking at surface area that the paint is going to be able to cover, that's how I'm going to determine how many quarts I need. So area is measured in square units anyway, so we want this to be a quadratic relationship. And we would want to overestimate so that we don't run out of paint.